Good morning, my name is Tamás.
Good evening, my name is Norbert.
I am pleased to be here. I am Johann Rafelski from University of Arizona, and I visit Wigner Institute and NEP Life project in order to learn and support the fusion program of the Hungarian government, which addresses the merger of nanotechnology, fusion technology, optical technology in search for novel paths to fusion, which could be used in civilian applications. One should always remember that in all nuclear physics applications, there are military and there are civilian uses. Just like with iron. If you forge iron, you can make weapons or you can make good things for life. And the same applies nuclear science, and the mistake perhaps commonly made, which I would like to avoid, is that what is good for weapons is good for civilian application. This is just not true. And one has to put a lot of good nuclear science back into action in order to gain technologies which could be used in nuclear fusion for civilian applications. And this has been, I would say, little recognized, and this is what drives the work of the Hungarian NEP Life project. The discovery of new methods and new approaches towards civilian application of fusion energy. And I think that's very commendable and has attracted my interest, and because I have been trying to help fusion path in civilian applications for the last 50 years. Despite the fact that most of my colleagues have this mix-up feeling that, oh, what's good for nuclear weapons, good for civilian applications, which is just simply not true.
So I absolutely agree with this education, and I would also say that the key problem which is coming to us and burdening more and more is the need for energy. And we have to find a way to give energy to the people, first of all in the form of electricity, because electricity can be very well distributed on networks and get into the final consumer. And that is also a goal of the civilian research in what we call nanofusion. Nanofusion has two origins, this name. One is that we want to use nanotechnology in constructing or experiments, and later smaller size devices which can make use of nuclear reactions, making electricity, and then use this electricity in a long-term and a flexible way.
There are many laboratories which nowadays are involved in trying to build up facilities for producing fusion energy, including laboratories where lasers are used. I think our unique possibility is that by combining with nanotechnology, we may scale it down to sizes which even in a small country like Hungary can be realized. Of course, this is not a simple issue, but a very promising one, a high risk, high gain possibility, and I think we are already in the phase where we can secure our priorities, that we are the ones who invented it, And therefore, maybe it is already time that we should open up and involve some other countries also international, make it more international in order to reach the target what we had in my mind a few years ago already.
My name's Chris. I'm the PhD student of Jan, and I came here to work on this project because I heard about it at a conference that I was invited to from Norbert and Thomas, and I found it extremely interesting. So as Jan was saying, most fusion projects that are around right now rely on organizing the targets, the different fusion systems on the scale of meter to micrometer, so 10 to the negative 6 meters. But this experiment focuses on structuring the fusion fuel on the nanoscale. And if the technology is available today to do this structuring somewhat cheaply, why not organize the fuel so fusion can be done more efficiently at this scale? It doesn't seem to me like there would be a reason not to. And I definitely agree with what Jan is saying, that a lot of these fusion experiments that are done right now are very large scale, very high energy. But we know we're going to need all sorts of technologies to solve the problems of the world. So the technology people are developing at places like NIF and at ITER, they're not going to be able to be used to say like do stuff like power a car, power a laptop, power a watch. We need different energy solutions for all of those different technologies. And this technology that we're developing here is of very high interest to me because it's more in the range of using lower energies to do very efficient fusion for more commercial applications rather than these large-scale projects.
I am personally very happy that almost from the very beginning we have some American involvement in this program. But nowadays it seems that some other countries are also approaching it. For example, Norway. This is something new, not only because one of our Hungarian partners is a professor in Norway, but seemingly the Norwegian country, state, has also some initiative which leads to joint efforts in this field.
Yes, we just got the news that they invent about 700 million into the nanotechnology related to laser experiments, and this is the entry port for nanofusion actually.
Okay. This really brings the question up, how is it done? And let me say a few words in this regard, because it explains why this is such a promising avenue. We are familiar with our cell phones, which have no antennas. And some of you may remember that not so long ago we were running around with cell phones where we had to extend an antenna out of the apparatus. And why did this disappear? Because people invented a method to attract in small antennas radio waves and focus them. And that's what we want to do with light. The nanotechnology is used in order to concentrate light beyond what we call diffraction limit, making high intensity areas of energy by building antennas for light and making these antennas for light react with and fuse. And of course not we don't want this to be done with nuclear weapon material. We want this to be done with other light elements. Fusion, unlike fission where we only have 2 or 3 suitable nuclear materials, fusion, amazingly, it is not well recognized, has dozens of suitable combination of 2 elements which can be brought together and fused with a very profitable energy gain. And recognizing this, there can be cycles of reactions which are very complex and which can be exploited. And what we are searching are cycles, just like in our sun, which do not produce neutrons. It's a little bit misleading what sometimes one sees in literature, that the current large machines are bottling the sun. First of all, they are much bigger than a bottle, and second, they are not at all operating on reactions which sun operates on. Sun operates, there's not a single neutron. Neutron is a particle we don't want to produce in nuclear fusion. It's the thing which makes the conventional nuclear reactors so dangerous. So we want to avoid it. Our sun burns hydrogen without production of a single neutron. It's quite amazing how the different cycles in the sun run and are not producing any radioactive byproducts. And we want to do the same in civilian application of fusion. And this has not been emphasized enough. And this is the opportunity to start afresh is presented by the nanofusion approach, because of the concentration of energy offered by antennas for light. And that's why marrying the good nuclear physics with good properties of nanomaterials is such an exciting opportunity today. And even young people see this instantly when they take a look at what's going on.
Yeah, I think we should mention too that the energy we're using is only around 10 times the power of a laser pointer you can buy off the internet, and just, a green laser pointer. But other fusion projects need to use millions of times more power than a laser pointer.
That's a very good point, Chris. Because of the concentration of light achieved with nanotechnology.
We're basically achieving the same energies as these other fusion experiments. We're just doing it on a much smaller scale, so we require less energy because we're focusing it to a smaller
But these are always methods that we call brute force methods.
Yeah, they're brute force.
Now, my experience in my life has been many times that whenever I succeeded to combine two different technologies successfully, then always something new came out of it.
Yeah.
Now, in this case, our advantage is that we succeeded, or on the way to succeed, to combine two technologies, nanotechnology and fusion. And seemingly the same advantages coming out of that also. And that's why we can do processes, and we in fact started to demonstrate it already, that the fusion processes at low laser intensities can be already realized. And that's for a small country like Hungary, especially a useful approach.